All right, welcome back to the session 4, Novel Materials and Devices. This session, we have 1 invited talk and 2 contributed talks. With that, let me introduce first speaker, Ali Javey is professor at the Electrical Engineering and Computer Science Department, UC Berkeley. He's also a faculty scientist at the Lawrence Berkeley National Laboratory. And also, he's a co-director of Berkeley Sensor and Actuator Center and Bay Area BB Consortium. Let's welcome Dr. Ali Javey. Today, he will talk about van der Waals heterostructures for tunnel transistor.
All right, well, thank you very much for the introduction. And I guess I have 1 hour, is that right? Only 1 hour. Okay, so I'm going to use the next 20 minutes to share with you some of the results that we have, the recent results that we have now on the use of 2-dimensional layered semiconductors for tunnel transistors. But before I start my talk, I have to acknowledge my students and postdocs. We are a group of about 30 students and postdocs coming from different departments: chemistry, material science, chemical engineering, mechanical engineering, of course, electrical engineering. And they all work together on the same projects in a very collaborative fashion. And specifically, the ones that I'm going to acknowledge the most for the purpose of this talk are the ones that are highlighted in bold. Mahmoud and Tanya have worked together to make some of our devices that I will present to you. Mateen, Danny, and Dai have done some brilliant work with surface passivation and defect repair in these materials. We collaborate with a wide range of folks here on campus, within E3S, and also outside. And finally, I have to acknowledge our current funding sources for this specific project, specifically NSF E3S and DOE Basic Energy Sciences. So with that, let me give you an overview of what we are trying to do. This is a research direction that we have explored over the last few years. I gave you an update on this a couple of years ago, 2 years ago at the same symposium. Then we had very preliminary results, and I will show you that we have advanced quite a bit since then. Of course, there are still a lot of challenges. And what we're trying to do is to use these new class of semiconductors, two-dimensional layered semiconductors, as the channel material for different applications, and specifically for tunnel transistors. These are materials that within each layer, the bonds are ionic or covalent. And between the layers, the bonding is covalent is van der Waals. The closest material that you probably know of that has the similar properties is graphene and graphite, except that these materials are semiconductors. And there's a whole library of them. They have band gaps, different band gaps, different band alignments. And really the unique feature is that you can achieve materials with thickness down to a monolayer with atomic level thickness uniformity. They do have defects. Of course, any material, regardless of how you grow it, always has defects. And I will share with you some very recent unpublished work. Given that these are monolayers and the atoms are all exposed, there are means and mechanisms to repair them. And I will show you one approach of doing so. And these two properties, in principle, can lead to sharp band edges in our semiconductors, and in principle, should lead to steep TFETs. And I'm going to highlight that a little bit later in the talk as well. And finally, because you have van der Waals interactions between the different layers, in principle, you can build heterojunctions with different crystal structures, so you're not confined to some of the lattice constraints that you are often limited to for conventional semiconductors. But before you start thinking about making a complex tunnel transistor with these materials, you really have to think about controlling the various material properties. And over the years, we have done a lot of work looking at how we can dope these materials, how we can form contacts, what's the effect of strain. And most recently, we have looked at the defects and what's the role of defects, how do we eliminate them or how do we reduce them. And we have also looked at the heterojunctions. For the heterojunctions, we have looked at various fundamental material properties and processing issues. We have looked at interlayer coupling. Do they couple if you have one layer on top of the other, coupled through van der Waals forces? And most recently, we have also shown that you can build tunnel devices. So over the years, we have developed this toolbox, and that's really how I like to think about it. You know, we really take it for granted that if you work with 3.5s or silicon and germanium, some of these properties, of course, are well established after decades of research. For these new semiconductors, these are not established, so we had to first look at some of these fundamental issues. So let me share with you just some highlights. Because of time constraints, I cannot, of course, talk about all the work that we have done, but let me just show you some of our previously reported materials progress. We looked at different schemes of doping them, p-type and n-type, to different doping levels. We developed ways where the doping is stable over time, air stable. And we looked at 3 different mechanisms. One of them is surface charge transfer. You can just put down different species on the top, depending on whether they're electron withdrawing or donating. You can dope them either p-type or n-type. We have shown that you can put down a film with fixed charges and do remote field effect doping. And we have even explored covalent functionalization as a mean of doping these materials. We've looked at the effect of strain on the band structure. And one particular example that is unique and interesting happens to be tungsten diselenide. If you have a monolayer of tungsten diselenide and it's relaxed, it is known to be a direct bandgap material. But as is the case for most of these materials, if you make them into multi-layers, then they become indirect bandgap. And so here what you're looking at is the photoluminescence count as a function of the light intensity. And you can see that the monolayer has a very strong emission peak. The bilayer is the solid line, and it has a very weak emission peak. It's indirect. But what we showed is that if you apply strain, tensile strain, we can go from indirect to direct. So that's a knob that we have. It's very similar to germanium. You can do the same thing with germanium. And we have demonstrated this with these chalcogenides as well. We've also looked at how we can build transistors where all the components, the source drain, the channel, gate dielectric, and the gate are made of layered material. So we have figured out ways to transfer these and to build transistors where really all the junctions are based on these van der Waals interactions. But a work that I want to share with you and highlight the most is the most recent work that we have done on understanding the defects, characterizing the defects, and eliminating the defects in these materials. And of course, defects are very important. I think we will have a session tomorrow on tunnel transistors, and we will talk about the effect of defects and trap states on tunnel transistors. But it is now widely established that today's tunnel transistors are limited largely by the mid-gap states caused by traps within the material at the junctions. If you have a perfect semiconductor, of course, you have in principle, you have a sharp conduction band edge and sharp valence band edge, and you have no states in the middle. But in reality, that's not what we typically have. We have semiconductors with defects, and these induce different trap states, and these trap states can reduce the steepness of your devices, specifically tunnel transistors. So the question is, of course, how do you probe the defect density? How do you see if you have a lot of defects in your material? And there are different schemes of doing that, but the easiest one that people have used, of course, with conventional semiconductors extensively is to use photoluminescence, and specifically photoluminescence yield as a metric for characterizing the defects and figuring out how much defect you have in your material. And the concept is very simple. If you grab your material and you pump it, you shine light on it, you will generate electrons and holes. And in the absence of defects, all of the electrons and holes that you generate will eventually recombine and give you a photon out. So for every photon coming in, for every photon getting absorbed, you emit one photon out. The quantum yield, the photoluminescence quantum yield is expected to be 100%. That's if you have a perfect semiconductor. If you have defects and you have these different trap states, then of course they will induce non-radiative recombination, and that will reduce your quantum yield. So by measuring the quantum yield, you can probe the defect density in your material. So we started looking at our materials, and we measured the photoluminescence spectrum. This is the steady state photoluminescence spectrum for moly sulfide, and this is a monolayer moly sulfide. The blue line is for the monolayer as made, and in this case, you don't see much of an emission. The pump intensity is very low in this particular case, but in fact, there is some emission. If you zoom in and you normalize it, you do see some light coming out, but it's very weak. And we have recently developed a process, a very simple process. You treat these monolayers in a special chemical, and what we have found is upon exposure to this chemical, the shape of the spectrum doesn't change, the normalized spectrum, but the intensity dramatically gets enhanced. So now you have a material that is emitting a lot of light out. And this is really clearly seen in the case of a monolayer that is patterned into these three random letters, CAL. And you can look at the photoluminescence map, and that's what you're looking at here. So the color here corresponds to the photoluminescence intensity that you're measuring. This is as made, and upon treatment, you can see that it's glowing. There's a dramatic enhancement in the photoluminescence. So we did more quantitative analysis of the quantum yield, and here I'm showing the quantum yield as a function of generation rate. This is basically the illumination intensity. What was the pump power that you put in? And you can see that for as-made moly sulfide, the peak, the highest value that we could observe, that we could measure, is a little bit less than 1%. And in fact, different crystals have different quantum yield values. We've seen anywhere between 0.1 to 1%. And people in the literature had reported similar values. So the quantum yield is very low. If it's 1%, that means that 99% of the carriers are recombining non-radiatively. So after treatment, after this chemical treatment, if you measure the quantum yield, you can see that now we can achieve close to 100% quantum yield. That's the red line. And the quantum yield at the beginning is independent of illumination intensity, and then you have this drop that takes place. And the dashed line is actually the models that we developed. We worked with Eli. This was work that we did in collaboration with Eli Jablonowicz. And my student Mateen developed this very simple model that, in this case, the dashed line corresponds to what you would expect out of an ideal monolayer material and an excitonic material. And the reason why you see this drop is because at very high concentrations, carrier concentrations generated by light, you have an effect that is similar to OJ, not exactly. It's a bi-excitonic recombination. Two excitons can recombine together. And amazingly, of course, the lifetime is dramatically enhanced as well. You can see that before the treatment, the lifetime is very poor, 180 picosecond. It goes all the way up to 8.5 nanosecond. And if you think about it, this is quite incredible. You have a material that is only 0.7 nanometer in thickness. It's just a monolayer. And it's optoelectronically perfect. That means that all the recombination is taking place radiatively. We have also looked at other metrics to characterize the quality of the material. Another metric that you can look at is the Orbach tail. So you can get the implied absorption coefficient as a function of photon energy. And the slope here would give you the Orbach tail or the band edge sharpness. Here you can see that for as exfoliated MOS2, the value is respectable. And if you treat it, the value drops down even more. So the band edges are becoming sharper as well, which you would expect if you were treating the defects. Stability is pretty important. If you leave these samples in air, just exposing it to whatever is happening in the lab, no special care is taken here. You can see that the luminescence efficiency remains high even after a week, and actually after even a few weeks, it remains the same. So there is no change in the luminescence efficiency. So we are excited about this because we think that we have now a material that in principle no longer has those defects and no longer has those trapped states. This is a recent work, so we haven't really applied that to different devices. But in the meantime, we have done in parallel to all this material knowledge that we have gained over these individual components, we've also done a lot of work with various heterostructures. And let me share with you some highlights for our heterostructure work. This was something that we reported last year. Actually, we reported it 2 years ago at this event. So I'm just going to show you one summary slide. We built a heterobilayer consisting of a monolayer of tungsten diselenide stacked on a monolayer of moly sulfide. So that's really a heterojunction at its scaling limit. That's the thinnest you can get. And what you're looking at here is the high resolution TM. You can clearly see that in the heterojunction area, you have this moire pattern. It's a clean moire pattern, which means that at least within the region, within the size, the area that you're looking at, that you're resolving under TM, you have a very clean interface. The moire pattern is coming about because you do have a angular rotation between the two materials, and also they have different lattice constants. We studied the various properties of these heterobilayers, and one that I'm going to highlight was looking at the photoluminescence. If you look at the photoluminescence, which is the solid line spectrum for monolayer moly sulfide, you get a peak emission at about 1.9. If you look at tungsten diselenide by itself, you get a peak emission at about 1.7. And interestingly enough, for this heterobilayer, you get a new peak, a new PL peak that is at lower energy, and that's about 1.55 electron volt. And so we looked at this more carefully by doing absorption studies and also by doing XPS microscopy. And we figured out that basically this is the type of band offset that you have in this material system, in this heterobilayer. And there are really three different processes that are taking place. The absorption is spatially direct. Each material is absorbing light. So you're getting electrons and holes generated and excitons generated within each material. Because of the band offset that you have, and because every electron and hole that is generated is really at the interface, they don't have to diffuse to reach the interface. They're monolayers. Electrons will all pile up in moly sulfide. Holes will pile up in tungsten diselenide. And then you get this emission that comes about from this transition labeled as number 3. So the emission is spatially indirect. And it's very strong in intensity, which is indicative of a strong interlayer coupling. We have a lot of charge transfer taking place, and also carriers are combining at this interface. More recently, we reported tunneling diodes using these material systems, and this is the first device structure that we reported. We proposed this idea again at the same event 2 years ago, but it took us a couple of years to actually make it functional. And this is a work that my postdoc Tanya did in collaboration with my student Mahmoud. And the device structure is as follows. This is a bilayer device. You have tungsten diselenide as one of your material. The other one is moly sulfide. You have two gate structures. You have two gates, one on top, the other one on the bottom. They're symmetric gates. And the purpose of the gates is to control the carrier concentration, the doping effectively, and the band alignment in each of these two layers. So you can readily control how the bands are aligning and whether you get any currents between them, whether it's a reverse bias tunneling current or a forward bias current, by just controlling the two gates. There is no doping involved. And that's a unique feature. And ideally, you want to move away from doping because doping does induce, in principle, band edge. It reduces the band edge sharpness. That's well known. So this is a high-resolution TM of the device. You can clearly see the heterobilayer. There's the bottom gate, top gate. It's a symmetric device. And Tanya and Mahmoud measured these devices. It's effectively a 4-terminal device, so you can do, of course, a lot of different measurements. And I'm showing you one simple measurement that we did where we fixed the gate voltage to MOS2 such that MOS2 is electrostatically doped to N+, and then we are varying the gate voltage for tungsten diselenide as we measure ID VD. So in this case, we applied a small gate voltage to tungsten diselenide, so effectively you have a P- N+ diode, just a normal PN junction. And what you measure is that in the positive voltage, you get a large forward current, forward bias current. And in the reverse direction, you get minimal current until you reach this breakdown voltage, beyond which we see band-to-band tunneling. So we can then increase, of course, the gate voltage on the tungsten diselenide to make it more P-type. As you make tungsten diselenide more P-type, you can clearly see that the forward bias current is the built-in voltage is increasing, and you can see that in your current characteristic. And the onset of tunneling, the breakdown, is now getting less. You can increase the tungsten diselenide voltage even more. And as you do that, now you can see that within the voltage range that I'm showing, up to 1 volt, in the forward bias, you're not measuring any current. You're limited by the noise floor of the system. And in the reverse bias, you have large tunneling currents taking place and band-to-band tunneling. So this is now a backward diode. So we went from a normal PN junction, a normal diode operation, to a backward diode where you don't have current in the forward bias, but you only have current in the reverse bias. And of course, you can apply even larger gate voltage. And if you do that, now you have an N plus P plus situation. And you can observe NDR, negative differential resistance, in the forward bias. And you can clearly see that. And that NDR, of course, is gate controlled. Depending on the gate voltage, you can shift the position of the NDR peak and the peak to valley ratio. So this was the first observation of building such a device, where you have 2 separate gates, electrostatically doping your 2 different layers, and operating this diode in different regimes, ranging from a normal diode, backward diode, and a Saki diode. More recently, we have looked at other material systems. The previous case, moly sulfide tungsten diselenide, we saw tunneling current, but it was really a good diode only. We had to apply very large gate voltages because of the band offset to be able to get band-to-band tunneling. So we have started to look at other material systems, and now we have found a new combination where you get a type 3 or close to type 3 band alignment between the 2 to start with. So using this structure, of course, it's much easier to observe band-to-band tunneling at lower voltages. And this is now our device characteristic. I'm showing you ID versus VG. You have the P branch. In this case, the P branch corresponds to the tunnel FET operation. You have the N branch that corresponds to the MOSFET operation. For these devices, always you typically see both branches, and depending on how it's biased, one branch usually will be the tunnel device, the other branch will still be your MOSFET, the normal MOSFET. Now what I'm showing you here is the temperature dependency of this device. If you look at the P branch, which is the tunneling current, there's absolutely no temperature dependency. The swing is not changing, the current is not changing. Now if you look at the N branch, which is your MOSFET region, the swing is changing as expected with temperature. And so this is really a clear indication that we have tunneling on one side and you have a normal MOSFET operation on the other. And the other indication that you can use, the other indicator, is to look for NDR. And if you cool down these devices, you can often observe NDR in the forward bias direction if you bias them properly. Now these devices that we have, our first generation devices, the swing is about 100 millivolt per decade, and it's a 2D TFET. It's actually the first demonstration of a 2D to 2D TFET. So this is just a highlight of what has been reported in the literature for 2D heterostructured devices in terms of band-to-band tunneling. I talked about our work, which we published in January. Since then, there have been other publications in the field. including some work done at Penn State where they used the AFM as a contact, and also at Cornell where they were able to measure NDR, observe NDR at room temperature. But these devices were just two-terminal devices. They didn't have gate. So in our case, we had, of course, gate control. It was gate control tunneling. But that's the 2D, of course, is one system that you can explore. The other system that, that we have explored in the past is doing 2D, 3D. And here, 3D, I'm referring to the use of conventional semiconductors like silicon, germanium, indium arsenide. And we reported a couple of years ago, back in 2013, one example system, indium arsenide, tungsten diselenide. And you can clearly see from the TM, high-resolution TM, that you have two different materials with very different crystal structures. This is your indium arsenide. This is tungsten diselenide with the layered structure. You can clearly see the individual layers. And we reported a diode. This was the IV characteristic of this device. And it was just a diode, and the diode had an ideality factor that was very close to 1. And that was just, for us, quite amazing that you could achieve such a high-quality interface using this system. And that's a system that can also be interesting to explore in the future. And there have been also other work using this platform. And I talked about our work that we published in 2013 for indium arsenide, tungsten diselenide. Since then, there have been multiple works on crystalline silicon moly sulfide. People have also observed p-n junctions. And most recently, just yesterday, actually, in fact, there has been interesting results from Santa Barbara where they used germanium moly sulfide, and they were able to see band-to-band tunneling, and they reported pretty steep swings at low current levels. So this is a field that is moving very rapidly. There has been a lot of progress. There has been a lot of progress with understanding the fundamental material properties and controlling them. And, but of course, there is still a tremendous amount of challenge that is left. We're really excited about the fact that we can now control the defects. The device work that I showed you was done without fixing the defects. The defect repair is we just figured it out. So we're going to start to apply that technique to our devices to see if we can improve the interfaces and device qualities. And it looks interesting, but of course, as always, there are a lot of challenges ahead in improving the on-currents, the swings, moving forward. And with that, thank you very much.
All right. Thanks, Ali, for great work. I think interest time. Okay, just quick question. One question only. All right.
What kind of defects were there that were fixed, and how were they fixed?
So good question. So from various studies by different groups using STM, for example, the people have characterized the different defects, specifically vacancies. It's known that these materials have a lot of sulfur vacancies. And the sulfur vacancy formation energy is a lot lower than moly vacancy. So you have a lot of sulfur vacancy in these. And so we are still not sure about the chemistry. We know about the physics. We are certain about the physics. The luminescence yield is 100%. We have been able to model it. The chemistry part, we have tried to understand exactly what is happening. It's difficult to understand. I always say this, the amorphous silicon, people have been hydrogenating it. And still to this day, it's very debatable what is hydrogen doing in that material. So it's very difficult to really understand what is happening on the surface. But our thinking right now is, by working with some of our chemists, including Felix Fischer, who is also a part of E3S, sitting back there, is that we think that we are repairing the vacancies. So we think that we are filling the vacancies. It's too early to claim that, but most likely that's what we're doing.
Okay. Let's thank speaker again.
Thank you.